technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job? To redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. Today, I am pleased to be talking with Dr. Gordon Keeler. Gordon, who knew he wanted to be a scientist by the time he was in second grade, joined DARPA as a program manager in the agency's Microsystems Technology Office in 2017. His work is all about exquisite control and management of electrons and light within device-loaded chips and otherwise compact systems that can do more computing, more sensing, more decision-making, more artificial intelligence in cheaper, smaller, lighter, and more energy-efficient packages than any technologies we have had in hand before. To me, his deliverables represent a pinnacle of the entire history of technology. Prior to joining DARPA, Gordon spent 14 years at the Department of Energy's Sandia National Laboratories in Albuquerque, New Mexico. There he became good friends with semiconductor lasers, modulators and detectors, nanophotonics and plasmonics phenomena, semiconductor materials and device physics, radio frequency and ultrafast optics, novel photonics materials and their integration with existing platforms, and microscale optoelectronic packaging technologies. Earning his first degree in physics in Canada, where he grew up, Gordon in 2013 earned his PhD in applied physics from Stanford University. Along his career path, Gordon has published more than 100 peer-reviewed publications and has been granted several patents in the field of photonics. Dr. Gordon Keeler, thanks for making some time to talk with me today about your ongoing adventure in technology development.
Thanks, Ivan. It's great to be here.
I always love to hear about the origin story of a person's interests, and I think listeners do too, especially when those interests are hyper-specialized in the eyes of most people. I mean, I think we agree most people have probably never even heard the term optoelectronics. And you told me in earlier correspondence that both your father and mother got you going in the science and engineering directions that you would ultimately take. So I'm hoping you might share with us a little bit about what it was like, what kind of encouragement you got in your childhood household, and then also what other influences you think of when you might explain why you think the way you do think now.
Sure. Well, I grew up in Canada, like you mentioned, in a relatively small town. My parents really both loved exposing us as kids to lots of different things. So I was busy, doing sports and music, but I really loved academics. My mom was a teacher and a librarian and a nurse. My dad was a university physics professor. And so, academics was sort of really important in our family. As far as science, I really loved problem solving when I was a kid. And I also liked building things. When I was little, I used Lego blocks. And as I got bigger, I used Meccano, which here we call erector set. And so, tiny little nuts and bolts and putting things together was sort of my specialty. And really that's sort of what my career looks like. I do a lot of problem solving and building tiny little things.
Yeah, fascinating to think about the erector sets, which had macroscopic parts. I mean, you could actually manipulate them with your hands. And when I think of the devices and the parts that you're working with now on the micrometer and smaller scales, it's just kind of astonishing. Now, you spent 14 years at Sandia, one of our national labs, and I would guess that while there and maybe even before you had heard about DARPA, but I also do like to share with listeners the how did this particular program manager get to DARPA story. And so what's that story for you? Was it somebody you knew at DARPA? Did you, in a sense, let DARPA know about you and your interests? How did you get here?
Yeah, it's a little bit of all of those. Back when I was in grad school, I actually worked on DARPA programs. I guess that was my first introduction. But then I got to Sandia. I worked on a lot of different technologies in this optical microsystem space. And I was there for, like you said, 14 years with my wife, who also studied applied physics and did a lot of building of small things. I got a call from the MTO, Microsystem Technology front office, saying that the director wanted to talk to me. And I thought, well, that's interesting. He's probably looking for a reference for somebody that I work with. who was looking to move to Darpa. And it turns out, no, actually, they had seen some of the work that I was doing, and they wanted to know if I wanted to come to Darpa, which, I was very familiar with Darpa, but hadn't really thought about coming to be a program manager. But, given that opportunity, I thought about it really hard, really quick, in fact. We had to make a decision pretty fast and came out and interviewed, and things moved quick. Picked up the family and moved out of New Mexico and came out to the East Coast. So I've been at Darpa since 2017.
So that's a big decision. I mean, one thing that always amazes me about program managers is that, you come in knowing that this is almost certainly not a lifelong appointment. In fact, one of the pieces of the secret sauce, one of the ingredients of the secret sauce of the organization is that, you come in knowing that you're just going to be here for 3, 4, 5 years, that sort of thing. Some people do, of course, come back for second tours of duty later. But tell me just a little bit about, why you had so much confidence and sort of excitement about coming to Darpa that you were willing to leave a place you'd been for 14 years and then go to one where you might only be there for a few years.
Yeah, it's a great question. I had no doubt really in my mind. Darpa was clearly sort of the pinnacle of doing innovative scientific research and development and leading the community to go do new things. That had always been my passion. And I didn't go into science and technology for a stable long-term job at one place. I wanted to make an impact, and Darpa was clearly the way to do that. What comes next, we don't really know, but I feel like my life has been this series of fortunate events that kind of stack up, and I'm sure there'll be great opportunities after I'm done here.
Well, may that good fortune continue. So, Gordon, now let's dive into your portfolio of programs. When I look at the half dozen or so of the programs you have taken on, I think one of them has gone to completion, that they're thematically connected in several ways. One of them has to do with the design and integration of micro devices that manipulate and manage electrons and photons, but also connecting all of the technology work that you're doing is it kind of another sort of technology advancement that I've seen at Darpa can be even more consequential than, say, an initial invention. And I'm talking here about a term that we hear and you hear in technology circles called C-SWaP. That's C-SWaP. It refers to the challenge of taking or transforming what originally are sort of big, expensive, power-hungry technologies and making them smaller and lighter and more energy efficient and cheaper. And this then opens them up to kind of wider access because, say, they're cheaper and not so unwieldy. And essentially, you're taking something that's impractical for many and making it more practical. So it's those kind of two themes that I see. And if you keep those in mind, and feel free to bring other themes in as well, take me and listeners on a tour of your programs.
Sure. Yeah. Well, the term C-SWaP that you bring up, it stands for cost, size, weight, and power. And it really is a way to quantify the benefits of miniaturization. And if I look at the portfolio of programs that I've got, I'd say there's sort of two big themes. The first is generally optical microsystems. And the idea being, if we build systems out of very small components, integrate them together, then we can make them low cost, make them mobile, deploy them all over, and add new functionality. Typically, the way we do these optical microsystems is through another thing that's sort of a theme of my programs, which is heterogeneous integration. And that means different things to different people, but really it's about bringing different materials, technologies, and functions together into a really small package. We often think of many of these programs as creating some sort of capability in the size of a sugar cube rather than a beach ball.
One that goes back a ways is Moab. Let's start with that one. Modular optical aperture building blocks. And I remember first encountering this and thinking is sort of this remarkable idea of taking what might be a whole system of lenses, think of a telescope or binoculars, or those are more familiar ones, but then in a way flattening those down all into something like a more integrated kind of optical system that would be much less bulky than the originals. You inherited that, right? And so tell me a little bit about what you got, where you took it, and where it's at now.
Yeah, great. So Moab was one of the programs that I inherited back in 2017 when I arrived at Darpa. It's a great example of this optical microsystem integration concept. And the idea is that most of the LiDARs that we build today, this is a laser for 3D ranging. It's become really exciting and enabling for autonomous vehicle navigation, also used on your phone perhaps to recognize you. So typically, LiDAR systems that we use in the military are large systems. They have a telescope, they have a gimbal, and they're hand assembled, right? And so they tend to be big, slow, expensive. And so Moab is a program that looks to shrink all of that down onto a chip, sort of like a postage stamp, non-mechanical optical beam steering, particularly for LiDAR and other kinds of optical techniques. And a lot of this is done through integrated photonics, which allows you to take discrete optical functions like modulators or lasers, detectors, and put them into sort of micro scale, and then assemble them together onto a chip and maybe put thousands or tens of thousands of components on a chip that you manufacture in a semiconductor foundry, just like you do with integrated circuits. The program is now in phase 3, has made enormous progress. We've had many world records over the last few years scaling this technology, and now it's actually being flight tested and shows a path for doing things on small UAVs and other kinds of mobile systems.
Okay, and do you imagine that those kinds of systems are the ones where this technology will see at least its widest initial application, or do you imagine also that there are some other very big application areas down the line?
Yeah, that's a good question. And, I'd say that for most of the integrated photonics technologies that we look at, there is a very large commercial driver for most of the things that we pursue. And so if you think about the engineering cost of creating something like Moab, there's a whole lot of upfront development cost. Eventually, though, you get to the point where you can essentially stamp these chips out in a foundry. And it would allow you to scale these to sort of millions or hundreds of millions of units where the unit price can be very low. And so for Moab, the path there is for commercial automotive, where you can see, there are hundreds of millions of cars every year that need LiDAR systems that are small, compact. And so Moab might be good for the DoD initially and in certain cases, but also there's a path to commercialization and helping the broader community.
Very cool, very cool. So let me now move to another program that I've known about for a while. In fact, I even had met the program manager who started that one, Dan Green. So I'm referring here to CHIPS, which is Common Heterogeneous Integration and IP Reuse Strategies. So you don't have to actually parse all of that those words out. There's probably an easier way just to describe what the goal of that program is and what its status is.
So CHIPS is a program in our ERI portfolio, Electronics Resurgence Initiative. This is a number of programs that we're doing here in the office to help define what's next for semiconductor microelectronics. And CHIPS came about because there was an observation that, as Moore's law goes on and we can put more and more transistors on a chip, both the cost of fabricating chips at advanced nodes and designing them essentially puts the newest technology out of reach for both the military and for sort of moderate or small commercial uses. If you think about, say, the most advanced GPUs or CPUs built by big microelectronics companies.
And those are central processing units and graphics processing units?
Yep, that's right. If you think about these, they might cost a couple of $100 each, but the design time that goes into them, it can be thousands of engineering years. And so, if you want to put something on an aircraft, we can't afford to do that every time. So instead, CHIPS takes a modular approach, essentially a chiplet integration approach, where you don't need to create a full ASIC or application-specific integrated circuit from the ground up every time. Instead, you can compose a system out of smaller pieces where you really only have to create maybe a couple small capabilities, like a say, a machine learning accelerator chiplet or an RF radio frequency front end chip, and then assemble it with other things that are also in the CHIPS library and put it in a package. In fact, CHIPS has been a great success. It actually has transitioned over to OSD, where they have made a much bigger investment in the Navy ship program to try and make this a commercial reality.
And I will just remind readers that OSD stands for the Office of the Secretary of Defense. Now, as we continue the tour of your programs, let's move to PIPES, which stands for Photonics in the Package for Extreme Scalability.
PIPES is actually a really exciting program for me, and it's the first one I started at Darpa. PIPES is a program that is about a technology called optical interconnects. And that really means the technologies that you would use to send data from one chip to another with photons rather than electrons. Now, I started working on DARPA programs back in grad school at Stanford with Professor David Miller, who was an expert at optical interconnects. Optical interconnects were seen as sort of the future for microelectronics, but microelectronics kept moving forward without optics for a long time. Having said that, we've now gotten to a point where Moore's law has sort of put us into a corner. We can do more and more transistors and compute on a chip, but the wiring, or essentially the technology to move data around, doesn't really get better as you shrink it down. So you've got this bottleneck where you create all of this data on chip, but you can't move it from one place to another very efficiently. And we've reached a problem where we're both bottlenecked in terms of total capacity, and the energy that we use to move data becomes enormous and sort of dominates our system. So instead, we have to turn to a different solution, and optics is that solution. If you think about the internet or data centers, right, we've already used fiber optics to move data around for a long time, 20 or 30 years. And this has gotten meaningful at a shorter scale as we go forward. PIPES is looking to integrate photonics into the package, like it says in the title, for advanced microelectronic systems like CPUs and GPUs, which you defined before, or reconfigurable processors like FPGAs, which are field programmable gate arrays. FPGAs can be really powerful chips, but out of the box, they don't really do anything. They're meant to be programmed by the customer. And so they can really be applied to different scenarios, different applications. This makes it a really good application for the PIPES program. And so the program has a number of performers. They all have very challenging metrics, given that this field is relatively mature. So we're pushing Intel and Xilinx, two of our bigger performers, to put photonics into their most advanced FPGAs. They've actually had great success. We're just moving into phase 2. And then we have a number of smaller companies and academics working to really improve the underlying technologies, the integration, the circuits, the photonic components themselves, to help us as you go forward in time. So sort of 5 or 10 years out, these technologies are going to be particularly important.
Right. And there are so many interesting technical questions I could ask. I'm just going to sort of go to one just to give a flavor of the kinds of challenges you're dealing with. So like with optical fiber technology, I mean, that all emerged out of really kind of specialty, incredibly pure, glass. I mean, that's glass technology. Here, when you talk about optical interconnects and photonic components, I mean, just give us just a real short sense of what kinds of materials that you're actually talking about.
Sure. So we're talking about many materials, but usually they're at the chip scale. And so we have compound semiconductors like gallium arsenide or indium phosphide, often integrated with silicon, where silicon might be doing a lot of the electronics and the compounds might be doing emission and detection of light. And then those might be interconnected with glass fibers or other things that go between one source and one detector that might be a meter apart or a kilometer apart, depending on the application.
Great. Thanks for those details. Okay, now I would like to continue and talk about a couple of more of your programs. Next, let's move to Lumos, which I think maybe is one of your newest. This stands for Lasers for Universal Microscale Optical Systems. What are you up to with Lumos?
Yeah, so Lumos is the program that I most wanted to do when I came to DARPA. Lumos it's a heterogeneous integration program that basically integrates new materials in sort of a 3D way onto semiconductor wafers. And so if you look at integrated photonics today, it's moved very fast in the last decade because silicon photonics has been very successful. We use silicon in traditional electronic circuits, and by leveraging the fabrication techniques, people have moved silicon photonics forward very fast. You can fabricate really complex photonic integrated circuits. However, silicon's actually not a great material for optics. It's really good for fabrication, but it doesn't emit light, at least not very efficiently. It doesn't really detect most of the light that we care about. And it doesn't do other effects like nonlinear effects that we might care about. So Lumos is about integrating materials onto silicon or other low-loss materials, particularly to make lasers. So lasers and amplifiers in the optical space are really foundational. The laser was invented about 60 years ago, around the same time DARPA, actually.
They co-evolved.
Yes. And, people realized really quickly that lasers were going to be really important. They shrunk them down to make semiconductor lasers. And, we keep finding new applications for lasers. Silicon photonics doesn't really have lasers. And so you need to integrate separate laser chips to build up a system. So Lumos is saying, how do we put lasers directly on these wafers? And so the teams are doing various things. They're growing compound semiconductors right on top of silicon. They're integrating tiny little chiplets on silicon. They're doing nonlinear wavelength conversion so that we can create new wavelengths, maybe in the visible for quantum or atomic systems, and looking at how do you amplify light to get to sort of watts of power on these wafers.
Wow. So it sounds like tremendous amount of versatility, both kind of in the spectrum element and also power. When you think of 2 or 3 applications that would just tickle you if you saw them getting out there in real life, what comes to mind?
Well, so I think that there's going to be a lot of new applications beyond just moving data around, which is what photonics is used for today. So sensors for positioning, navigation, and timing. That's a big thing that we care about in the DoD, but understanding where you are and navigating in the world. Often we make precision sensors with quantum systems or atomic systems, and you have to interface with atoms. Every atom might be different. It might be a rubidium atom or a cesium atom. And Lumos is trying to address this by making a flexible platform that can create really narrow line width lasers at just about any wavelength that you care about on a chip.
Right. And is this where the optical frequency combs come in, which I've been hearing about and actually had a little bit of a challenge with a public affairs colleague of mine to see if we could, if you could describe that in a way that most people would understand?
Well, sure. I can give it a try. So, optical frequency combs have seen sort of a huge explosion of advance in the last few years. The idea is typically using nonlinear techniques. We go from a single optical frequency. If you think of a laser, it's sort of one single color. And we create a number of different frequencies that are all equally spaced in the frequency spectrum. If you think of them looking like a comb that you would, comb your hair with, each one of these tones equally spaced. This essentially becomes a very precise ruler, and it can be used in many different applications. It can be used for frequency metrology. It can be used for spatial metrology. And it's really created a whole new area of science and applications, including some of my other programs like Dodos and Griffin.
Okay, we'll get to that just in 1 minute. But I was thinking about these optical frequency combs the other day, sitting back on my deck, and I was wondering, if in addition to kind of specifying this, range of frequencies, if you can individually also determine and specify the intensity of each of those frequencies, because with that, then you'd be able to kind of simulate the color experience of any particular thing, like a leaf or wood, and the way each of those absorbs and emits a different portfolio of light frequencies. Can you do that with an optical frequency comb, or are all of those component frequencies, the teeth of the comb, as it were, or tones as you refer to them, are they all the same intensity?
Well, so typically they start out maybe similar in intensity, but you can certainly modulate each one of them and create just about any spectrum that you want. And so, one of the clear uses for optical frequency combs would be for spectral sensing. And so you could imagine creating thousands of tones at different frequencies and sensing maybe a gas plume and understanding exactly which molecules are present at what concentration by detecting the relative intensity of each one of those. We also have, under the PIPES program that I talked about, some teams that are using optical frequency combs with each comb tooth being sort of an independent source, almost like how systems today are built with individual lasers at different colors, wavelength division multiplexing or WDM. Instead, you could have one comb laser that creates hundreds of lines and then modulate each one, and now you have hundreds of optical channels, each carrying their own data.
Astonishing. So let's finish out your tour of programs with two that are related, and one preceded the other. I'm referring here to the two programs known as Dodos and Griffin, and I'll let you spell those out and tell me the technology trajectory that they amount to.
Sure. So Dodos is the direct on-chip digital optical synthesizer. This is a program I inherited also when I arrived back in 2017. It's a fantastic program, and it's a little esoteric, so for people that aren't in the optical physics space, it'll take just a minute to explain. But if you're familiar with microwave and radio frequency technologies, the direct digital synthesizer, or DDS, is commonplace today in a radio, in your car. You no longer have a tuning knob that you kind of have to tweak and find the right frequency. Instead, you just hit a button and your radio goes there. It generates the right frequency. Optics today is kind of still stuck in the microwave world of the 60s, where we build a laser and then we measure what the output wavelength is or the frequency. You might be able to lock it to something, but you don't really just tell it where to go. And Dodos, which is looking to make an optical analog of the DDS, is trying to do that. We just finished Dodos this year and made enormous strides. And the idea is, if you use optical frequency combs as your ruler and some microwave techniques where we know frequencies very well, hopefully you can create optical frequencies with incredible precision and accuracy. And so, in fact, under Dodos, we've seen many orders of magnitude improvement in the accuracy of optical frequencies. And this is all using chip-scale technologies. So again, trying to take technologies that today look like a room or a rack and put it into the size of a sugar cube.
Right. And just to help listeners who might be impressed that you can get the highest precision on a frequency, might be impressed by that capability, but doesn't know why. What do we get from that?
Well, sort of again, like changing the paradigm the way that digital synthesis did for radios. We also use optical frequencies for communications. And so you could imagine incredible improvements in optical communications by having precision control of frequencies at both ends, essentially doing coherent communications where both sides know what wavelengths are being communicated very precisely. Or you could do precision LiDAR, where maybe you have one source emitting and a different source receiving. It's also important for doing optical sensing, where you perhaps know the precise wavelength of different transitions for different molecules, or again, quantum and atomic sensors.
Okay, and then just one more point on this one, because as you were talking about, if I know and can produce an extremely precise frequency for communication, and I want my recipient to be able to do that same thing, or if my recipient can, that sounds like it would open up kind of privacy and security channels.
Yeah, that's a great point. You could certainly do that.
So Dodos was the prior program that led into Griffin. Talk about Griffin.
Right. So as we got near the end of Dodos, we saw this great advance in technology. In fact, I should say that under Dodos, perhaps the biggest outcome here was seeing the whole community get excited about nonlinear photonics. We had from the performers under Dodos, we had well over 100 peer-reviewed journal submissions, and we had more than 25 high-impact journals in the Nature and Science suite of journals. This is really changing the field, and there's whole sessions at conferences now on Dodos technology. Now, onto Griffin, which stands for Generating RF with Photonic Oscillators for Low Noise. It's a little bit of a stretch, but we like the name. The Griffin program is a recognition that if you can make extremely precise frequencies in the optical domain, and then divide those frequencies down from these sort of 100 terahertz frequencies down to the microwave, you actually reduce noise when you do that. And that means you can get incredibly precise low phase noise oscillators in the microwave regime. So oscillators are important in our entire world, right? They form the clock that drives every piece of digital electronics, your phone, your computer. Microwave oscillators in particular are important for communications and for radar. And so the DoD cares a lot about making very precise microwave oscillators. And they try and make them very low noise, very quiet, essentially. A pure tone, if you think of ringing a bell and just maybe, a crystal wine glass, that's a pure tone. At microwave frequencies, it is something that's sort of an exquisite oscillator, and it gets used in, again, exquisite systems. But using Griffin kinds of techniques or Dodos kinds of techniques, you can imagine making these exquisite oscillators not with RF electronics, which are often sort of hand-tuned, hand-built, expensive, bulky things, but putting them on a chip, and you use optics and photonics on this chip. But it's a case where we don't really care that there's optics inside the package. What we want to do is generate a microwave signal that ultimately comes out. So Griffin, again, with sort of this sugar cube idea in mind, has goals of making very, very quiet RF or microwave signals with optics inside the tiny box. And the idea would be we make better radars, better communication systems, and we can make them small, low power, and low cost. There's a lot of commercial applications as well, like imaging radar, say, for a autonomous vehicle. Or if you make it small enough, maybe it goes in every cell phone.
Wow. Okay. Well, Gordon, that was kind of an amazing tour of all of these programs. I mean, when I think of the technical challenges, when I think of the probably dozens of research performers who are working across these half dozen or so programs, and you keeping track of all of them and seeing how they can all integrate and synthesize, you have really got a lot on your shoulders. I give you some pats on the back for doing all of that, and it's exciting to think about the technologies that will move forward. So before we kind of come in for a landing here, I just want to see, was there anything that you thought of afterwards from any of these programs that you'd like to just share with listeners before I do take you in for a landing and liberate you?
So I think that there's a whole lot of unknowns as to where this technology could go, and there's a lot of potential. And so, I worry about occasionally on our Darpa programs, which are very focused, right? We're trying to solve one particular problem that we're missing things. There's other things like, biosensing or medical applications. And so we need to kind of look at the big picture and always keep looking for new opportunities. I would say that one thing I want to make sure that the listeners hear is that good ideas come from everywhere. And you mentioned the limited tenure that we have at Darpa. We're always looking for new people. And so if you've got ideas, I care a lot about optical microsystems, so for sure come see me if you've got ideas in this area. But get involved. Darpa is not one person or one place. It's a collection of people that are excited about moving technology forward. And so maybe you want to be a program manager, maybe you want to work as a CETA, maybe you want to be a performer and keep doing research, but reach out and get involved with Darpa.
All right, you hear that, listeners? It's a pitch for you guys to get in touch. And I should point out that the acronym CETA stands for the Scientific, Technical, and Engineering Assistants, who work with program managers like you, Gordon, to take programs through their entire life cycles. So, as I see it, you're kind of in the business of turning science fiction, or at least sort of visions of technology, into reality. And we've talked about a number of the ways you're trying to do that. But I'm wondering if, as a kind of a technophile and a technology developer yourself, do you dream about non-existent technologies, not yet here technologies that you wish were real things?
Well, right now, time travel, or maybe slowing time down. There's so much that I want to do. And, sometimes it's at work. Sometimes it's being at home with the family. Sometimes it's going and doing other things. And there's just not enough time. That would be it.
Right. So that would be a technology that would kind of end the lament that we all have, so many books, not enough time, so many careers to pursue, not enough, so many mountains to climb, not enough time. Gordon, I think if you can actually solve that problem, that's the one you will be most remembered for.
Right.
Though I don't think that's going to be a DARPA program as far as I know. Who knows? But you might be able to pitch that. To close, I just want to thank you for taking us on a tour of your life as a technology developer, as a program manager at DARPA.
Thanks, Ivan. It's been a pleasure.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. Thanks also to Tom Shortridge for his partnership in producing this program. For more information about Dr. Gordon Keeler, the programs he and his colleagues in the agency's Microsystems Technology Office run, and the many other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download this podcast, go to the Voices from DARPA page on DARPA's website.